with Liberty Mutual. And I think it's gone pretty well. It's been a joy to have Eric in the program. He's always been, it feels like, one step ahead of everything we've done. He's always asking questions, always wanting to learn more. And to give you a heads up, what he's going to be using in his presentation, he didn't even learn in this course. He wanted to do something to challenge himself, and so he's taken that on and learned most of it on his own. So he's a real go-getter. So I want to turn it over to Eric, and we'll see what you have for us.
Yeah, thank you, Meredith, for the kind words, and thank you, Brent, for getting us started here. So again, my name's Eric. Right now, I am a geospatial analyst with Liberty Mutual Insurance. I've been with the company for a little over a year, and in this specific role for about 3 months. So I'm really interested in using statistical methods with respect to geography, which helped inform a bit of my project that I'll be presenting today. Prior to being with Liberty Mutual, I went to The Ohio State University, where I graduated with a degree in economics with minors in Spanish and computer science in 2017. So I'm still just coming out of college and still trying to get my footing in the industry with an interest in, analytics and data science. So this course has been a really good opportunity to really hone those skills and get more experience working in more advanced statistical packages. So for my presentation today, I'm going to be modeling unemployment rates with a sort of advanced method called XGBoost, and we'll go more in depth about what that means throughout the presentation. So today we're going to start by talking about the problem, why it's important to model unemployment rates, and why it is a unique sort of issue to look into. We'll then go into my data gathering process, where I source my data from, then talk about aggregating my data and creating some variables in SQL Server. Then we'll go over some initial data exploration that I did to help understand my data better. We'll finally go into the final model with the machine learning XGBoost model, and then we'll talk about some conclusions from my model. So the problem I chose to focus on was predicting unemployment rates. Unemployment is of particular interest to businesses and government agencies, and is calculated by dividing the number of people above age 16 who are looking for work by the total sum of employed and unemployed people. People who are not actively looking for work are not included in this calculation. They would be considered not in the labor force. And we see that the unemployment rate on this graph at the bottom right peaked around 2009 in the height of the recession, and has been trending downward since then. The latest this graph shows is 2017, which had a 4.5% unemployment rate. It's still been coming down since then. I believe recent numbers from the Bureau of Labor Statistics show a 3.5% unemployment rate, which has many economists believing the economy has reached full employment, where just about anyone who is looking for a job can find one pretty quickly and easily. So modeling unemployment is a particular challenge and of a lot of benefit, mostly so that governments and employers can identify areas that will see continued economic growth, and gives a really good idea of how an economy is performing at both a local and a national level. So my data for this project came from the Integrated Public Use Microdata Series, or IPUMS. I used this website a lot in my college days, where I wrote a thesis on the interaction between African-American political leadership during Reconstruction and certain socioeconomic outcomes in the modern day. So IPUMS is a really great source because it uses data from the American Community Survey, which is an aspect of the census, and it gives us a 1% sample of all US households from 2011 to 2017. It goes back further, but my data focuses on this year range. It's really easy to use IPUMS because it has a cart-like system. So there's a screenshot at the bottom right that shows different variables that you can just add to your cart by clicking a button, and then it will prepare a data extract that you can just download pretty easily. So we'll be looking to aggregate this data to a county level. Again, it doesn't make a whole lot of sense to just model unemployment at a household or person level. We want to see it at more of a geographic level to draw more interesting insights. So in terms of data aggregation, it was necessary to take this really big data set, which is about 2 GB in size, and manipulate it into a format that's more easily uh, used by programs like R and Excel. So my data was aggregated to a county level from this household level, which necessitated us doing some feature engineering to change how we look at each variable. So on the top right, I have a table that shows how the data looked from a person and household level, and then how it looks at a county level. So for instance, we have an indicator variable called gender, which is 1 for male or 0 for female. We can't use that at a county level, so we needed to change that to % male at the county level. We also have things like average household size, average household income, and % of workers working part-time. Something to keep in mind as we move forward into the modeling process is that I split my data into 2 sets. 2011 to 2016 was considered a training set, and 2017 is our holdout or test set. Our goal is to predict unemployment for 2017 as accurately as possible. This sort of simulates a prediction type scenario where we're working with an unknown unemployment rate and trying to predict it given some data. We don't yet have data for 2018, but this might be something interesting to look into further with my model. So now we'll go into some quick exploratory analysis that I did on my data set, starting with the distribution analysis. I made histograms for different variables that I thought were interesting. So we'll start at the top left with the unemployment rate. We see this has a right skew with a center around 5%. But we see that some counties are experiencing unemployment rates greater than 15%. Household income shows a similar distribution with a center around $73,000, but there's a strong right skew as well. With some counties, the average household income is above $150,000. In terms of percentage of workers working part-time, this is more of a normal distribution with a center around 17%. Next, we'll go into some relationship analysis, just plotting 2 variables in a scatter plot to see how a change in one affects a change in another. So we see that overall, most of these distributions are pretty noisy, but some are showing some interesting relationships. So the top left, which looks to be the strongest negative relationship shown here, I have average household income plotted against unemployment rate. So it looks like counties where there's a higher average household income have lower rates of unemployment. The bottom left shows average home value by county, and there's a similar negative relationship as we get further out to the right, where it looks like counties with higher average home value are also experiencing lower unemployment rate. This gives me some indication that household income and home value are probably correlated, which we would probably expect. On the bottom right, we have percentage of workers working part-time. There does not seem to be a huge relationship here, although as we get further out to more people working part-time, there seems to be a lower unemployment rate, especially towards the outliers. This might be because these jobs are very low skill and there's less barrier to entry, so that people who are looking for jobs within their county might be able to find easier employment if it's much simpler to get a part-time job as opposed to a job that requires certain education or training beforehand. My final aspect of the exploratory analysis was to run a simple linear regression. So this helps us further understand the relationship between variables and unemployment. When we do the machine learning model, it's harder to interpret the effects of individual variables on the ultimate prediction. So this gives us a good idea of what we might expect to see once we create that machine learning model. So this table here shows different variables as well as the direction of their relationship. So this is basically the sign on the coefficient that comes out of the output. The actual effects of these variables are very small, in the orders of like millionths of a percent. So I left that out just in favor of the direction of the relationship. The far right shows the significance at different p levels. We see that our significant variables have p-values of less than 1%, which is what we'd like to see. It just means that the variable has a pretty strong relationship. So we see that household income has a negative relationship so that as household income increases in a county, unemployment will decrease. This is what we saw in the scatter plot, makes some intuitive sense. Home value, however, seems to have a positive relationship where an increase in average home value leads to an increase in unemployment. This goes against what we saw in that scatter plot, but this might be due to the fact that home value and household income are probably correlated so that they play off of each other and reach an overall effect together. Percent male has a negative relationship, meaning that as there are more males in a county, there are generally lower rates of unemployment. Age and percent part-time did not have a statistically significant relationship, which as far as part-time goes kind of reflects what we saw in the scatter plot where there's a lot of noise. Unemployment does not appear to be correlated with how many people are working part-time in a county. And household size has a positive relationship so that as there are more members in the average household, there is generally more unemployment. On the bottom, I have several measures of how well our model is fitting. On the bottom left is RMSE, which is the root mean squared error. It gives us an idea of how accurate our predictions are. So here it's 2.2%, which basically means that we can accurately predict unemployment within 2.2% of the actual, which given that unemployment doesn't have a lot of variation, especially over time, this isn't a really great job, but it's okay given our small data set and small amount of variables that we're looking at. Our R squared gives us an idea of how well our model is explaining the variation in unemployment, basically giving another idea of how predictive we are and if we can trust our output. So this is 0.33 about, which is pretty low. Usually when we're working with real life data, we'd like to see something above 0.4 or 0.5. On the bottom right is mean absolute error. So this is very similar to the root mean squared error, except it takes into account whether we are above or below the actual unemployment. So it's just another measure of accuracy or precision. So in this next phase, and actually before I start talking about building the initial machine learning model, can I answer any questions about my analysis up to this point? Okay, if not, then I'll just keep going. So to further refine our simple linear model, we're going to deploy an advanced tree-based model called Extreme Gradient Boost, or XGBoost. So this algorithm, and I'll go into it in more depth in the next slide, basically trains a random forest on a training set, then applies the model to a test set to make certain predictions. Here I have some code that demonstrates how I split my data set into the training and validation sets, as well as how I deployed that initial model to make predictions. So on the bottom of this slide, we have the same model evaluation metrics that I showed before, where the bottom left I have root mean squared error. This is 1.4%, so it shows that we're more accurate than our last simple linear regression model, but we could probably improve this still a bit more. Our R squared actually fell to 0.28, and our mean absolute error is 1.1, so it's still not doing incredibly well, but much better than just using the simple model, which shows the benefits of using machine learning over just making simple models in R. So on this next slide, we'll talk a little bit more about how XGBoost works. So Extreme Gradient Boost is an algorithm based on a random forest, which basically means that it creates multiple decision trees to model our data and then uses a boosting algorithm to give more weight to more predictive models. So essentially you can think of XGBoost as an aggregation of many smaller models to help create the most accurate prediction. So it seeks to minimize the error function of a given model. In our case, this is root mean squared error. And it will iterate over all of these trees to try and minimize that error function. And it also takes several parameters. And rounds is the number of iterations, the number of times we'll create this random forest in order to minimize that root mean squared error. There's also eta, which comes sort of from a neural network type approach to modeling, which is our learning rate. Basically that as we move from one iteration to the next, the algorithm will take a certain amount of information from the previous iteration. It's good to balance how much information we're taking from our previous iteration, because setting this too high can lead to overfitting, which is when our model knows too much about the training set and it actually will compromise its ability to predict on new data. Max depth adjusts the depth of the trees that we're creating within our random forest. More depth can lead to a more accurate prediction, but can also lead to that overfitting problem. Minimum child weight is the final parameter that adjusts how much weight is needed to generate a unique tree node. Basically, it's saying a decision tree can't make a rule that only affects maybe one observation, because that can lead to overfitting and generally makes our model more complex than it needs to be. On the right, we have a picture that shows different models being applied to the same box. So on the left is a model called D1, which is looking to classify whether our data in the box is a plus or a minus. So this one is a fairly accurate model for generating those positive observations, but leaves out 3 plus signs in the box itself. The second model takes a bit more of a heavy-handed approach and correctly classifies all of our plus signs, but actually leaves in a few negative signs, leading to inaccurate predictions. The third model is a bit of a mixed bag, where it correctly identifies 2 plus signs, but leaves in a minus and leaves out 2 plus signs. So each of these models are okay on their own, but the benefit of using XGBoost is that it would give different weights to each model to identify what it's good at, and then take an aggregation to more correctly predict the data that we're working with. So we see that box 4, which is the boosted model, actually correctly identifies all of the pluses and minuses within our box. So again, XGBoost is a really useful model because it uses so many smaller models to reach an ultimate conclusion that was more accurate in the end. So the final round of working with this machine learning algorithm was to tune our hyperparameters, which I discussed on the last slide. So using our MLR package, we can iterate over a set of possible parameters for XGBoost and find the final model that minimizes our error function the most. So we see on the left, there's a table that shows the different range of parameters that I iterated over to minimize my root mean squared error. Looking at max depth, child weight, eta, number of rounds, and then subsample. Subsample basically is a parameter that controls how much of our data that we're looking at in each iteration, so that working with smaller sets can actually lead to a better prediction in the end, but we also want to make sure that our model is working with enough data to create accurate predictions. So to the right of the table, I show some code that I use to create the learner that would then iterate over these parameters and then would return a final model that we could then apply to our test set. So we see here on the bottom, I have the same model evaluation metrics that we've shown before. Our root mean squared error has been minimized to about 1.1%, which is still pretty good, and I exceeded my expectations given how few variables there were in my data set to begin with. Our R squared is actually maximized out of all of these iterations, showing a 0.53, and that's pretty good. Working with real life data, we'd like to see something higher than about 0.5, so we can reasonably trust that our model is accurately reflecting the different components that cause variation in unemployment. Our mean absolute error drops to 0.8%, which is really good. Gives us an idea that we can accurately predict unemployment within about 0.8% up or down. So to go into some final conclusions from working with this model, we see that our final model has multiple advantages over our first, with a lower root mean squared error. Shows that working with a advanced machine learning type algorithm can give a lot of benefits for prediction over just building that simple linear regression. We also have a higher R squared, which shows that we can trust the results of our predictions much better with this XG boosted model than just our simple linear model. We also have more rigorous validation. So our XG boosted machine learning model was tested on training and validation sets, while the linear regression was just done on the full set. So the machine learning method more accurately reflects that real-world scenario where we have new data coming in and an unknown unemployment rate, and we'd like to see where that will go in the future. There's still a few opportunities for further analysis for my project. So our model should be checked for overfitting. As I mentioned throughout the presentation, this is when we can actually hurt our predictiveness of the model by training it too much on data that will cause the model to just exploit different patterns. And one way to assess this would be to bring in new data. So right now, as I mentioned, there's no 2018 data available from IPUMS, but once that becomes available, it would be really interesting to run my model on that set and see how predictive it can be. One final step would be to visualize our predictions on a map. Using a map would allow us to see if there's any inherent biases or help us understand the implications of our predictions. So one issue might be that maybe my model really accurately reflects unemployment in urban areas, but rural areas, because there might be thinner data, might have more inaccurate predictions. So once we can identify those problems, you can then deploy different methods to help address those. So that about wraps up my presentation and my use of the XGBoost machine learning model to predict unemployment. Can I answer any questions people might have about my analysis?
Eric, fantastic.
Thank you.
Hey, Eric, it's Doug. I was curious if you could speak to a little bit about the explainability of your XGBoost model as compared to your linear regression model.
Yeah, definitely.
Good job. That's path.
Doug brings up a good point that, it's a little bit harder and more of a black box when you are using a machine learning model to make predictions, because we can't really say, okay, if you experience this kind of level of percentage of males in your county, that leads to this much unemployment. There's not as much output that really gives you an idea of how each variable is related. So that's why it's really useful to make the simple linear model before you start with the machine learning, just so that you understand the basic relationships between your variables and your target variable.
Very cool. Yeah, I love the idea, and we always like to ask that question of kind of if you had a little bit more time or a few more weeks, and you mentioned in your further analysis the third bullet about the map visualization opportunity, and that would be a really cool piece to, like you said, to see demographically in different markets and things like that, kind of where things fell. So yeah, very, very cool concept. So do we have any other questions for the group? Meredith, anything you'd like to add?
No, you've done an absolutely wonderful job, Eric. You've been peppered with questions from me for a long time, so I'll leave you be.
Awesome. Yeah. Thanks, Meredith.
Great, great. Well, do we have any other questions from the group before we, Eric was gracious enough, little did he know it, to go first today, and we certainly appreciate that. So before we let him off the stage, do we have any additional questions from the group?
Hey, Eric, it's Ashley, one of the directors here at Woz U. I just wanted to compliment you on your presentation skills. You did an excellent job. You articulated your points in your presentation very well. So well done.
Thank you. Yeah. There's no further questions. I just have one slide. Just thanks again to the Woz U team for your support and educational materials. I learned a lot just getting those reps in R and Python and other sorts of analytical platforms. Definitely learned a lot from the program, and really was able to challenge myself and identify areas that I'd like to get better in. And it's really applicable to the work I'm doing right now at Liberty Mutual, and was a big fan of what I was able to take away from the program. Also, big thanks to Meredith, who's been there, the whole way, providing mentorship and additional advice. Like she mentioned, I came into this project saying I wanted to challenge myself and work with a model I've heard a lot about but didn't have a lot of hands-on experience with. And just being able to talk through certain problems with her really gave me good direction and gave me a good idea of how the presentation should work out. So again, thanks a lot to Meredith.
Well, great, Eric.
My pleasure.
Yep. Well, thank you again, and obviously thank you, Meredith. And I think that's just not only a testament to your hard work, but yeah, to the just your willingness to take the instruction, take the advice, the support, the mentorship provided by Meredith. That was a phenomenal presentation, and great things ahead for you at Liberty Mutual. So you are off the stage, my friend. So we would love for you to stick around and see these other presentations. But with that, we will let you stop screen sharing and give Devin an opportunity to set up his screen, and then we will move forward with Devin's presentation.
Great,
Meredith,
thank you.
would you like to introduce Devin as well?
Absolutely.
Okay, I'm gonna mute, and we will